Welcome to this lecture. My name is Mark Scythian. The date today is November 27, 2025. So in this lecture, we're going to cover fundamentals of fluid dynamics, focusing on airflow, the application on the left in the first video. In the next video, we will solve the water flow application on the right. So on the left, we have an airflow application involving a forced air induction blower with a 500 cubic feet per minute airflow rating. The lowercase q represents airflow, and water flow is always represented by capital Q. So this forced air induction blower is operating under an atmospheric pressure of 14.2 psi and an air temperature of 62 degrees Fahrenheit. So it's discharging forced air above atmospheric pressure across a 2-foot diameter circular duct, which then tapers down to a 1.75 foot diameter circular duct and then out the outlet nozzle. So in the airflow application, we are going to calculate the absolute pressure and initial velocity V1 discharging from the blower, traveling upward 18 feet and then flowing into a constricting or converging duct with a final V2 velocity and absolute pressure at the outlet. So the first step is to calculate the cubic feet per second airflow. So we just simply divide the CFM rating into 60 seconds. So we get 8.33 cubic feet per second airflow. Next, we solve for the V1 or the initial velocity. So that is the Q rating, the airflow rating in cubic feet per second divided by the cross-sectional area, in this case, of the 2-foot diameter circular duct. So we have to solve for the cross-sectional area at the 2-foot diameter circular duct. So we use pi r squared, 2 feet, divide that into 2 to get radius. We square the value and then multiply it times pi. So we calculate 3.14 square feet of cross-sectional area at the 2-foot diameter circular duct. So that is known as A1 in this case. So we can divide the 8.33 cubic feet per second into A1. Units cancel out into feet per second. So we calculate 2.65 feet per second for V1. So the airflow is discharging out of the blower at 2.65 feet per second. Next, we can solve for A2, the cross-sectional area at the 1.75 foot diameter circular duct. So we divide the feet diameter into 2 for radius squared, then times pi. We calculate 2.41 square feet cross-sectional area, or CSA. So next we can use the continuity equation, which is A1 times V1 is equal to A2 times V2. So we can solve for V2. So algebraically this is rearranged so it is A1 times V1 divided into A2. So A1, 3.14 square feet cross-sectional area times V1, 2.65 feet per second airflow discharging from the blower divided into the cross-sectional area at the 1.75 foot diameter circular duct. So this calculates to 3.45 feet per second for V2. So next we have to solve for the gauge pressure at P1. If we add this to the atmospheric pressure, then we calculate the absolute pressure. So we can take a piece of the Bernoulli equation, which solves for dynamic pressure, 1/2 rho v squared. So the rho symbol here is the Greek letter rho for the fluid density, and fluids include gases and liquids. So in this case, the rho represents the air density in slugs per cubic foot units, or slugs per cubic foot unit. So in order to solve for the air density first in pounds per cubic foot, we have to use a very common equation in chemistry for solving for air density in pounds per cubic foot. So we can multiply the molar mass of air, 29 grams per mole, times the atmospheric pressure in PSI, 14.2 in this case, and then divide this product on the numerator into the ideal gas law constant for air, 10.73, then multiply times the absolute air temperature, in this case the absolute Rankine's temperature across the airflow at 62 degrees Fahrenheit. So Rankine's absolute temperature is the sum of the degrees Fahrenheit plus 460. So when we work this ratio out, we calculate an air density of 0.0735 pounds per cubic foot. And then there is 32.2 pounds is equal to 1 slug mass in the US system of measure. So we simply divide the pounds per cubic foot air density value into 32.2, and this yields 0.00228 slugs per cubic foot air density at 14.2 psi atmospheric pressure and 62 degrees Fahrenheit relative temperature. So we keep that away for the rho value. Now we can solve for our gauge pressure at P1. So where V squared represents V1 squared. So P1 gauge is equal to 1/2 times the air density, then times the V1 quantity squared. And we calculate a very tiny gauge pressure of 0.008 psig. So the sum of the gauge pressure and absolute pressure, the sum of the atmospheric pressure plus the gauge pressure is the absolute pressure. So we have our absolute pressure, PSIA, is equal to the gauge pressure plus the atmospheric pressure. So we can take our gauge pressure and add it to our atmospheric pressure. So we calculate 14.21 PSIA for P1. So now we can move on and use the Bernoulli equation to solve for P2 with respect to the 18-foot altitude increase. There will be a pressure drop. And we have all the information to solve for P2 using the Bernoulli equation. So we have P1 plus 1/2 rho air density times V1 quantity squared plus air density rho times gravitational acceleration times H1. So that's the start height at 0 feet, made equal to P2 plus 1/2 rho air density V2 quantity squared plus air density rho times gravitational acceleration, then times h2, height 2. So that's 18 feet. So if we work this out by substituting our calculated information, we have 14.21 plus the quantity of 1/2 or 0.5 times the air density, then times the V1 quantity squared. So we calculate this value and then we add it to the rho GH1. So rho air density times gravity, then times height 1 is 0. So this cancels out to 0. So we add these three up together and we get a value of 14.22, for which we make equal to P2, then plus 1/2 times air density, then times V2 quantity squared, so that's 3.45 feet per second quantity squared. So when we work this one out, we get this value here. Then we add this to air density rho times gravity, then times height to 18 feet. And we get this value here, or these values here, and then when we add these two up together, 0.013557 plus 1.32, we get this value here, 1.33. So now all we have to do is subtract 1.33 from 14.22 to calculate P2, and we calculate 12.89 PSIA, absolute pressure for P2. So next we can round to one significant digit, the final values. Then we can place the label units on the drawing to finalize the calculation. So this ends the airflow fundamentals of fluid dynamics lecture, and I'll see you in the next video and we'll solve the water flow application on the right here.